Good morning. My name is Karolina-Towards and I'm representing AGH University of Krakow in Poland. And today I would like to present the results of my works which I conducted with my colleague Tomasz. And we called this research as Towards a Solution for the Pre-Failure Concrete Element Crac Detection Problem. At the beginning, I would like to focus on the problem statement, and we assume that narrow cracks as cracks with a width not exceeding 0.3 millimeters, which means that they are very difficult to recognize, so other features of the concrete are more significant. And the second thing is that they are very beneficial for us to recognize these cracks because they can be considered as part of the pre-failure state diagnosis. And the second important thing for us is that content is everything because narrow cracks can be part of surface problem. And what is most important, the sign of crack given by length and width means something completely different depending on the location and element of the bridge on which it occurs. And why we are dealing with this problem? Because cracks is a natural phenomenon occurring in concrete. And our aim during the design and during the construction is to not exceed this limit value of crack's width, which I mentioned previously is 0.3 millimeters. I will give as an example one type of crack damages that occurs in bridges. Many bridge components are massive, so the ratio of the area to the volume of the component is small. And one of the main problems in the technology of massive elements is the fact that as a result of the ongoing cement hydratation process, the temperature inside the element rises to the maximum and then falls to the same temperature as the surroundings, causing that occurrence of tensile strength exceeding the strength of the young concrete. At the same time, shrinkage effects occur, resulting in cracking of the maturing element. And as you can see on the slide, in a simply supported element during the heating phase, the center of the element heats up to a higher temperature than the edges, which causes that edge zone to stress. And in the cooling phase, the center of the element shrinks to a higher temperature than the edge, causing the middle zone of the element to stress. We consider these problems as inference based on machine learning models for segmentation problems. And this research presented here is based on two datasets. The first is an open access dataset that we authored, and it concerns problems observed for the concrete surface using RGB or monochrome cameras. And the second dataset is related to the concrete cracking process associated with the corrosion of the reinforcement inside the concrete. And this dataset is provided by our colleagues from Shenzhen University in China. And these datasets are not similar regarding the problems. What is the same for those datasets is that they are related to segmentation problem, and they are small datasets, not big enough to train big machine learning models. And what are the differences between those datasets? Our dataset is a binary segmentation problem, for now at least. And this dataset is focused on cracks, on surface cracks, and other features are not recognized here. This dataset is dedicated also for classification. So it's the segmentation and classification dataset. And this dataset is an open source. You can download it from Zenodo. And the Chinese dataset is related to the multi-class segmentation problem, and it focuses on corrosions. It is only related with segmentation problems, and if you want to use it, you should send a request to the author. And the corrosion is related to material crack. And as you can see in the example in the table, our images are sub-images in size 224 by 224 pixels. And the second data set consists of almost 20 images of a cross-section view of the concrete sample, which are split into sub-images in the monochrome channel during preprocessing. And conclusions regarding the surface crack datasets are based on the dataset, which has not been augmented in our case, while the data on the damages with the concrete were augmented due to the small size of the dataset in the Chinese problem. On this slide, you can see examples of the types of damages that can appear on the concrete surface and which are shown in our dataset. What is important, our dataset has been prepared, as I previously mentioned, as a binary dataset. It is not prepared as a multi-class dataset. And in particular, I want to pay your attention to the damages marked as B and C, because their features from machine learning point of view are very similar to the cracks, which can be confusing for the network. Today we will be presenting solution for the segmentation and not the classification of images, but segmentation is nothing else than classification at pixel level, and we will refer to metrics that are the results of confusion matrix. Going to the Chinese experiment, our colleagues based this experiment on making a concrete sample with a rebar inside. It was subjected to an accelerated corrosion and XCT test. For details of this approach, I refer you to the publication, and the dataset that has been made available to us consists of images with masks containing 6 classes of damages. On this slide, we present the research result of Chinese colleagues. In order to test our pipeline, we carried out a self-implementation of the approach using PyTorch Lightning, Hydra, and Optuna. However, our implementation was prepared from the point of view of concrete surface cracks, so the comparison of effects is shown by multi-class average, but as you can see, we obtain a little bit better results. And going to the results of our network, this slide shows that results corresponding to true positive and false negative, which give satisfactory results. The next true positive results, which also include more challenging images, which are more difficult cases, and automatically performed feature engineering gives different results because the network detects cracks where, despite the direction, it does not learn only a single pattern, for example, a vertical crack. Here we have some examples of different problems when we have different disturbance. For example, in the first example, we have formwork marks, and the second example, we have concrete voids, and in the third example, we have a complicated background, and our network is recognizing cracks well also in these cases. On this slide, we present examples of linearly characteristic elements. and despite their trajectory characteristics is close to the Cracs, they are not recognized by our network as false positive results, which is very satisfactory for us. And examples of false positives that are not affected by surface artifacts. Going back to the next steps, we would like to think about the situation when, depending on the damage location of the structure, the learning strategy of the solving network cannot be the same. So we propose a different balance of precision and recall metrics depending on the importance of the occurrence of a given crack on the bridge element. And the solution of this problem can be achieved in two ways. The first way is to build a dedicated metric, and the second is to build a relation based on the proportion between precision and recall metrics and integrating into the loss function. And the consequence of this approach will be, in the first, increasing the solution granularity significantly and better fitting the problem at a given bridge location, and the need to develop metrics and train dedicated models for different bridge elements. And going to the technology stack, we use three main approaches. The first is that the hyperparameter optimization framework to automate hyperparameter scratch, and this framework is used Bayesian optimization instead of standard grid search for hyperparameter tuning. The second thing is that we use open source framework to dynamically create a hierarchical configuration by composition and override it through config files and the command line. And the third thing is that we aim to design and create deep learning models that can easily run on distributed hardware while keeping the models hardware agnostic, since we not always work in coherent environment. And our aim is to making deep learning experiments easier to read and also to reproduce. And we have put a lot of effort into creating a robust and generic training workflow. So the first thing is the ability to train our own architectures and use fundamental models. The second thing is efficient parameter space search using Bayesian optimization. And the third thing is implementation of the architecture was carried out in a parametric manner. And the aim of our approach is to optimize the solution presented here and to easily adapt and compare results for both binary and multi-class problems using different models. And thank you for your attention.